Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar, Haryana. Today we are going to discuss about the module Introduction to Lasers from paper Atomic, Molecular and Laser Spectroscopy. We'll be able to understand the development of the lasers and its timeline, laser light, transition probabilities and population inversion, stimulated absorption, spontaneous and stimulated emission, difference between laser light and ordinary light, properties of the laser light, directionality, intensity, monochromaticity and coherence, and above all self-focusing of the laser light. It is very important to understand the development of the laser and its timeline starting way back when Max Planck received the Nobel Prize in Physics in 1918 for his discovery of elementary energy quanta. In his most important work published in 1900, Planck reduced the relationship between energy and the frequency of radiation, saying that energy could be emitted or absorbed only in discrete packets, which he called quanta, even if the chunks are very small. Albert Einstein in 1905 realized and mentioned in his paper on the photoelectric effect that proposed that light also delivers its energy in chunks, and these discrete quantum particles now we call photons. In 1917, Einstein proposed the process that makes lasers possible due to stimulated emission. He gave a theory that besides absorbing and emitting light spontaneously, electrons could be stimulated to emit light of a particular wavelength. April 26 in 1951, Charles Townes of Columbia University in New York conceives his maser idea while sitting on a park bench in Washington. Maser is a name for microwave amplification by stimulated emission of radiation. In 1954, working with Herbert J. Zager and graduate student James P. Gordon, Townes demonstrates the first maser at Columbia University, and the ammonia maser, the first device based on Einstein predictions, obtains the first amplification and generation of electromagnetic waves by stimulated emission. 1955, at PN Lebdev Physical Institute in Moscow, Nikol Basov and Alexander M. Prokhorov attempt to design and build the oscillators. They propose a method for the production of a negative absorption that was called the pumping method. And in 1956, Nicholas Blomberg of Harvard University develops the microwave solid-state maser. September 14, 1957, Townes sketches an early optical maser in his lab notebooks, and in November 13, 1957, Columbia University graduate student Gordon Gould jots his ideas for building a laser in his notebook and has it notarized at a candy store in the Bronx. It is considered that the first use of the acronym laser was done at that time, and Gould leaves the university a few months later to join private research company TRG, Technical Research Group. 1958, Townes, a consultant for Bell Labs, and his brother-in-law, Bell Labs researcher Arthur L. Shallow, in a joint paper published in Physical Review Letters, show that masers could be made to operate in the optical and infrared regions and propose how it could be accomplished. At Lebdev Institute, Basov and Prokhorov also are exploring the possibilities of applying maser principles in the optical region. December 1960, Ali Jaman, William Bennett Jr. and Donald Harriet of Bell Laboratories developed the helium neon laser. This laser was the first to generate a continuous beam of light at 1.15 micrometers. 1961, lasers begin appearing on the commercial market through companies such as Trine Instruments, Perkin-Elmer, and Spectra Physics. March 1961, at the Second International Quantum Electronics Meeting, Robert W. Hallworth of Hughes Research Labs presents theoretical work suggesting that a dramatic improvement in the ruby laser could be made by making its pulse more predictable and controllable. He predicts that a single spike of great power could be created if the reflectivity of the lasers and mirrors were suddenly switched from a value too low to permit lasing to a value that could. A high fineness optical cavity consisting of two mirrors traps and accumulates the photons emitted by the ion into a mode. The ion is excited cyclically by an external laser, and at each cycle a photon is added to the cavity mode, which amplifies the light. So, in 1962, groups at GE, IBM, MIT, Lincoln Laboratory simultaneously developed a gallium arsenide laser. 1964, the carbon dioxide laser is invented by Kumar Patel at Bell Laboratories, the most powerful continuously operating laser of its time. It is now used worldwide as a cutting tool in surgery and industry. In the same year 1964, the ND-YAG laser, neodymium doped YAG laser, is invented by Joseph E. Jozek and Richard G. Smith at Bell Labs. The laser later proves ideal for cosmetic applications such as laser-assisted in situ keratomal LASIK vision correction and skin resurfacing. In 1975, first quantum well laser operation made by Jan P. van der Zijl, R. Dingley, Robert C. Miller, William Wegman, and W. A. Nordland Jr. The lasers actually are developed in 1994, December 2009. Industry analysts predict the laser market globally for 2010 will grow about 11%, with total revenue hitting $5.9 billion. January 2010, the National Nuclear Security Administration announces that NIF has successfully delivered a historic level of laser energy more than 1 megajoule to a target in a few billions of a second and demonstrated the target drive conditions required to achieve fusion ignition, a project scheduled for the summer of 2010. The peak power of the laser light is about 500 times that used by the US at any given time. March 31, 2010, Rainer Blatt and Paito Skimt and their team at the University of Innsbruck in Austria demonstrate a single atom laser with and without threshold behavior by tuning the strength of atom or light field coupling. Introduction to lasers. Laser, we all understand, is a common name, but it is abbreviated for light amplification by stimulated emission of radiation. And there are basic components of the laser system. First is an active medium of the atoms or molecules through which the laser will be generated. A mechanism for creating population inversion, wherein we require a greater population of electrons in an excited state that existed in the lower state. That means completely inverting the population from lower state to the excited state. A resonator or cavity which has resonant frequency equal to the photon frequency. Transition probabilities and population inversion. Assuming that there are n atoms in equilibrium with a radiation field and considering electron transition between two quantum states, the upper state being labeled 2 and the lower state being labeled 1, now there are n2 atoms instantaneously in the upper state and n1 in the lower state. The population n1 and n2 may change in three ways as has been depicted in the figure: stimulated absorption, spontaneous emission, and stimulated emission. The emitted photons have random directions and phases, and the radiation is said to be incoherent. In the stimulated emission process, the two photons have the same phase and direction, and a beam of such photons is said to be coherent radiation. And transition probability is expressed in terms of the photon density per unit frequency, joule per cubic meter per second. The rate of change of N1 is proportional to N2. If N2 is equal to 0, that is no electrons in level 2, that means spontaneous emission does not occur. The constant of proportionality is the Einstein A coefficient. dN1 dt is equal to plus N2 A21, number of spontaneous downward transitions per second. The rate of change of N1 due to stimulated emission is proportional to the product N2 into PV. If there are no electrons in level 2 to be stimulated or no photons to stimulate them, then stimulated emission doesn't occur. The constant of proportionality is the Einstein B coefficient, labeled as B21, or which has the same units of B12, which was the case of absorption. Thus we have dN1 upon d2 dt is equal to plus N2 B21 PV, number of stimulated downward transitions per second. Therefore, the total rate of change of N1 is given by dN1 by dt is equal to N2 A21 plus N2 B21 minus N1 B12 PV, number of transitions per second to and from level 1. Under thermal equilibrium conditions, N1 and N2 are related and the Einstein coefficients. If the atomic system is in thermal equilibrium with the radiation at a given temperature T, the relative population of any two energy levels such as 1 and 2 are given by Boltzmann equation. So N2 is equal to e raised to the power minus E2 upon kT is equal to e raised to the power minus h nu upon kT, which is a state of thermal equilibrium, and N1 is equal to e raised to the power minus E1 upon kT, where k is Boltzmann constant and N2 is less than N1. Also, under equilibrium conditions, the net number of downward transitions must be equal to net number of upward transitions. N2A21 plus N2B21 PV is equal to N1 B12 PV, again making the thermal equilibrium condition. So there applies the principle of detailed balance that states that for thermal equilibrium, every process must be balanced by its exact opposite. Now, solving for PV, one obtains PV is equal to N2A21 divided by N1 B12 minus N2 B21. The units can be derived by using the above equations. PV is equal to A21 by B21, 1 upon B12 upon B21 e raised to the power h nu upon kT minus 1. Again the units can be written. We all know Planck's formula for emission of black body radiation by a body at temperature T is PV dV is equal to 8 pi nu square upon c cube h nu upon e raised to the power h nu upon kT minus 1 dV. And in order to agree with Planck's formula, the following equation must hold good. B12 should be equal to B21 and A21 upon B21 is equal to 8 pi h nu cube upon c cube, and so we get these equations. And it is worth noting that in 1917 Einstein derived these equations, but he did not know how to calculate the A and B coefficients. The calculation of these coefficients is a quantum mechanical time dependent perturbation theory calculation, and quantum mechanics was not developed until 1926. The 1932 Nobel Prize in Physics was awarded to Werner Heisenberg of Germany, and for this creation of quantum mechanics, the application of which has inter alia led to the discovery of allotropic forms of hydrogen. The 1933 Nobel Prize in Physics was awarded jointly to Erwin Schrödinger of Germany and Paul A.M. Dirac of Great Britain. For the discovery of new productive forms of atomic theory, Heisenberg developed matrix mechanics, Schrödinger developed wave mechanics, and Dirac developed relativistic quantum mechanics. The development of quantum mechanics led to the calculations of Einstein coefficients, and B21 in the electric dipole approximation is written. B21 is equal to 2 pi square upon epsilon naught h square psi star ER psi 1 dV square. dN1 upon dt is equal to N2 8 pi h nu cube B21 plus N2 minus N1 B21 PV. So, number of transitions per second 2 from level 1. Further, dN1 upon dt is equal to N2 minus N1 B21 PV. So, this clearly mentions that the condition required for lasing action from the active material is N2 greater than N1, which is contrary to the thermal equilibrium distribution as we had discussed about above. This condition is called the population inversion. And a metastable state is a state from which all transitions to lower energy states are forbidden. A metastable state has a long lifetime in microseconds, particularly approximately 10 to the power minus 3 seconds, and atoms making upward transitions due to collisions or radiation absorption tend to accumulate in metastable states. An ordinary state has permitted transitions to lower energy states, and hence it has a short lifetime around 10 to the power minus 8 seconds. Now, the properties of laser light. There are 4 properties. One is directionality, the other is intensity, the third one is monochromaticity, and fourth one is coherence. So, we will be discussing one by one all. Directionality. The directionality of laser beam is expressed in terms of full angle beam divergence. That is twice the angle that the edge of the beam makes with the axis of the beam. The outer edge of the beam is defined as the point at which the strength of the beam is dropped to 1 by E times its value at the center. As the beam moves straight and only in one direction, the laser beam can be sharply focused, while light from an ordinary source travels in all directions, and in latter case the energy intensity rapidly decreases as one moves away from the source, similar to the fact that sun's intensity diminishes when it finally reaches the earth. This simply means that a laser beam can give very high energies to a very small area. The second important property is of intensity. The intensity of a laser beam is quite high in comparison to any other light source. As the laser gives light into a narrow beam, its energy is concentrated in a very small region, and this leads to great intensity. Now we have output intensity per unit area that is highly directional and very large. Now the flux densities for focused laser light of 10 to the power 15 watt per centimeter square are achievable. However, an oxyacetylene flame has a flux density of only 10 to the power 3 watt per centimeter square. An object needs to be heated to a temperature at around 10 to the power 30 Kelvin to radiate with an intensity of a typical laser source. It is worth noticing that tungsten lamp, while radiating, is only at 3000 Kelvin in temperature, and our sun is only about 10 to the power 8 Kelvin. If a point source is radiating energy in all directions, producing a spherical wave, and is assumed that no energy is absorbed or scattered by the medium, then the intensity decreases in proportion to distance from the object squared because of the inverse square law. Applying the law of conservation of energy, P is equal to integral I dot dA. P is equal to I A surface is equal to I dot 4 pi r square. I is equal to P upon area surface is equal to P upon 4 pi r square. For a monochromatic propagation wave of Gaussian beam, if E is the complex amplitude of the electric field, then the time averaged energy density of the wave is given by U is equal to n square epsilon naught upon 2 E square, and I is equal to Cn epsilon naught upon 2 E square, where n is the refractive index, C is the speed of light in vacuum, and epsilon naught is the vacuum permittivity. The third important property is the monochromaticity. A laser source is highly monochromatic, means comes with a precise wavelength, while ordinary light source has a broad spectral output. The spread in frequency of a line is characterized by the line width. The laser light has a high degree of monochromaticity. A typical laser emits line of line width as 3 angstrom. It is almost the purest monochromatic light available so far. In fact, lasers can be generated with short time durations from picosecond to femtoseconds, and this can be considered dual property of monochromaticity. This means the energy concentrated in wavelength. Looking at the important property of laser, which is coherence, laser light has high degree of coherence, whereas the ordinary light is not coherent. This is the unique property of laser beam. It has arisen due to stimulated emission process. The emitted photons have a definite phase relation to each other. This coherence is of two types, temporal coherence and spatial coherence, both of which are important. Ordinary light is not coherent because it comes from independent atoms which emit on time scales of about 10 raised to the power minus 8 seconds. Though there is a good degree of coherence in sources like the mercury green line and some other useful spectral sources, but their coherence is not comparable with that of a laser. As we discussed that there are two types of coherence, one is spatial and the temporal. The figure depicts the difference between spatial and temporal coherence very beautifully. Electric field distribution around the focus of a Gaussian laser beam with perfect spatial and temporal coherence is shown in the figure. A laser beam with high spatial coherence but poor temporal coherence can be visualized in the figure. And a laser beam with poor spatial coherence but high temporal coherence can be again seen in the figure. And it is important to tell that spatial coherence can be visualized by Young's double slit experiment, while the temporal coherence can be visualized through Michelson interferometer. In conclusion, the high degree of collimation has arisen due to the fact that the cavity of the laser has very nearly parallel front and back mirrors which constrain the final laser beam to a path which is perpendicular to those mirrors. The back mirror is almost perfectly reflecting while the front mirror is around 90% reflecting, but the light has passed back and forth between the mirrors many times in order to gain intensity by the stimulated effect of more photons at the same wavelength. The highly collimated nature of the laser beam contributes both to its danger and to its usefulness. One should never look directly into a laser beam because the highly parallel beams focused on the retina of the eye will cause instant damage to the retina. Lasers have one more important property of self-focusing of laser light. The laser is known to be a nonlinear phenomena and therefore has a unique property of self-focusing. Eta is equal to 1 plus xi under the root. A dielectric medium, when placed in an electric field, it gets polarized. Each constituent molecule acts as a dipole with a dipole moment pi. The dipole moment vector per unit volume P is given by P is equal to summation pi. Orienting effect of the external field on the molecular dipoles depends both on the properties of the medium and on the field strength, and therefore P is equal to epsilon naught into E. Here epsilon is called the polarizability or dielectric susceptibility of the medium. With sufficiently intense laser radiation, the relation doesn't hold good and has to be generalized too. So there are many terms in the series. P is equal to epsilon naught chi 1 E plus chi 2 E square plus chi 3 E cube and so on. Now the medium is called a nonlinear medium. Therefore, considering P1 is equal to epsilon naught, chi1 plus 3 by 4 chi2 E naught square into E. The expression for the refractive index is therefore eta is equal to 1 plus chi1 plus 3 by 4 chi2 E naught square, and this term 3 by 4 chi2 E naught square along with chi1 can be termed as chi nl. Therefore, eta becomes chi1 plus chi nl. So, chi L is equal to 1 plus chi1. That gives the dielectric permittivity of the linear medium. And epsilon NL, that means for nonlinear part, it comes out to be 3 by 4 chi2 E naught square. This is nonlinear increment in the expression for dielectric permittivity, and therefore N is equal to NL 1 plus NL E naught square, where NL is the refractive index of the linear medium and the NL is nonlinear increment in the expression for the refractive index. So NL E naught square is equal to epsilon NL upon twice epsilon L under the root, which is equal to 3 chi2 E naught square upon 8 1 plus chi1. This implies that the refractive index of a nonlinear medium is proportional to the square of the amplitude of the field, that is, to the intensity. Now, the intensity of a laser beam is not constant over its cross section. It peaks at the axis of the beam and falls off gradually away from the axis. The velocity of the light wave is given by V is equal to C upon eta. As eta decreases, owing to the falling of the intensity of the light beam, plane wave front incident on material becomes concave as it propagates through the medium and contracts towards the axis and therefore self-focusing. The figure very well depicts the self-focusing of the laser beam. If we send a laser beam through telescope from Earth to Moon, then when it reaches to Moon, it covers approximately 2.5 miles diameter circle. Now, what will be the divergence angle? As we know that the distance to the Moon is approximately taken as 2,50,000 miles. Therefore, divergence angle phi is equal to 1.25 miles divided by 2,50,000 miles, which is equal to radius of beam oblique distance covered, and it comes out to be 0.000005 radians, which is equal to 5 rad. Now, coming to the next corollary, compute the energy difference between upper and lower energy levels of helium neon laser, and the wavelength of helium neon laser is considered to be 632.8 nanometer, and one can very well calculate the energy 1240 divided by lambda, and it comes out to be 2 electron volt. In this we have learnt the development of laser in chronological order. Laser is a system consisting of 3 components: active medium, mechanism for population inversion, and cavity or the resonator that has resonant frequency equal to photon frequency. We have also understood the concept of transition probability and Einstein coefficient, the different properties of laser that make it superior than ordinary light. Coherence is the important property due to which laser can be used either for dangerous things or usefulness. Self-focusing of laser light is an added advantage. Thank you.